All right, so I actually brought the slides, not intentionally. We were talking about compound homogeneous transformation. We said the story is basically that if we are transforming coordinates between multiple frames, not just two frames, and that's the gist of it. That's the story of compound homogeneous transformation. What do? We just go with pairs of frames. Every two frame, we find a transformation matrix between those two. And from there, the story is just a matrix multiplication. Just as always, we end up doing math. And we said, or I said that it's very beneficial if you have a point in a coordinate frame that is multiple frames away from where you are. And it happens a lot when you're studying robotic arms or generally mechanisms in robotic. You're going to end up having multiple coordinate frames for different reasons. You're installing a sensor somewhere, you have an actuator in another place, you have to control that, you have to get the signal or control the motion of the actuator. So there are so many reasons for that. But you're going to end up having multiple coordinate frames, and you want to be able to move from one coordinate frame to another easily, either from the last one to the first one, the last one to somewhere in the middle, from the middle one to the last one. You might want to have this freedom to move between coordinate frames, right? We said this whole transformation matrix, compound homogeneous transformation, better to say, helps us to deal with this process, right? I went over an example, the general procedure. The second example was more detailed, simpler. I would say mechanism is just basically a two-link robotic arm, if you want to think about it that way, or it's just simply just a two-link mechanism, two links mechanism. We did this one. Yeah, we actually finished this one. Now I want to do another example. Well, a couple more examples, but another example along this line, then another example expanded on this. Oh, let's see how things go. So for this one, that is a very large size one. So for this one, let's let me bring, if I can find where it is. Hopefully that's the example 8, right? I'll bring it, and yes. So we have a SACAR robot arm, SACAR mechanism, let's say. We actually talked about this way at the beginning when we were talking about different mechanisms. We talked about this one. I'll put it here, SACAR. And you remember at that time I told you do not ask me again what does SACAR stand for, because I just remember it in that class, and after that I just don't remember. Just take a look at your notes. But that's common in manufacturing environments. You'll see this mechanism in different forms, in different, I would say, ways of assembly, but same mechanism in manufacturing environments. In this case, you have, let's just look at the system itself. So you have a revolute joint here, right? The green part, you can think about this axis Z, right? The green part, or not the green part, let me be more accurate. So this link right there, this one, can rotate around Z, and the rotation is represented by theta1. Right? So we can have a rotation in this direction. So it's a revolute joint, right? This joint right there, I'm going to make it so ugly at the end of this. This joint right here is a revolute joint. Right? So it rotates, the link right there can rotate around the green link right there, so as a fixed link. Now we go one step further, right? This link right here can rotate around Z1, right? And the angle of rotation could be theta2. So we have another revolute joint here. This is going to be the axis of the joint, right? This is the axis for the first joint. The rotation occurs around it. You're talking about the revolute joint, right? So if your thumb is the axis of rotation, or your thumb shows the axis of rotation, when you have a revolute joint, assuming that your four fingers are representing the direction of the rotation. You usually go with right-hand rule, so things are pretty established, and we can come up with uniform, I guess, procedures.
Quick question, Professor.
Go ahead.
So imagine that we all know what the right hand rule is.
Mhm.
Just for like being thorough, if you want to explain that just one more time in case someone doesn't know
All right.
what the right hand rule is.
Yeah, I hear you. So I wasn't really, but I wasn't really going into right-hand rule, I guess, even that much. We were just talking about the joints in terms of joints. So all you need to know is just we have two joints, two type of joints that we're going to work with in this course, right? Revolute and prismatic. And we said revolute joint we represented with just a cylinder, and that would be the axis of the joint. Now, if you think of this as a revolute joint, the rotation of the cylinder, any cylinder, you can think of it even your pen as the joint. The way they represent it is just a cylinder. Now, the rotation of that, if you represent the rotation with your four fingers, right, let's say it rotates, in this case, it rotates, let's go with counterclockwise this way. If I have a camera, so let's say it rotates this way, all right, counterclockwise. Now, if my four fingers follow the direction of the rotation, right, goes this way, so my four fingers follow that. My thumb shows the axis, or the other way around. If my thumb is the positive direction of the axis, right, it's all about positive and negative. Later on, you'll see that. So if I have my axis, in this case, if I have my axis, already made it ugly. So if we have Z1 right here, and it's upward, right? This is where Z1 is. Yeah, somebody should stop me from making things crowded. So this is Z1, right? It's upward. So if this is the axis of your, this is what you need to know when it comes to robotics and positive and negative. Hold your thumb in the direction of the axis, the positive direction of the axis. This case Z1. Later on we'll see how do we define x1, y1, z1, x, y, z, x2, y2, z2. Right now we are one step into the process. Somebody already defined these axes for us, put it here, put it on these joints, and now we are working with it. Now, when we go further after our exam, we'll start talking about if you're given an arm and you want to study its kinematics, where to start. Where do you put the coordinates? How do you define? How do you figure out the orientation of these coordinates? Right? These are things that we will decide. You have to decide, and we'll figure it out. Right? For now, we are looking at one step further. Somebody figured it out, put the axes there, x, y, z, x1, y1, z1 for each, and we put one axis on one coordinates on each joint. Right? That's typically how it is. Somebody did that for us. Somebody put x, y, z on the first joint, put x1, y1, z1 on the second joint, which is a revolute, and x2, y2, z2 on the third joint, right, which is a prismatic joint. It elongates this way, I believe. I have to double check this problem statement. It elongates, can go either way, up or down. Shorter or longer. We do have a revolute joint here, but they didn't put an axis coordinate on that. We'll talk about the rules. How do we actually come up with a uniform method of putting coordinates? Now, at this stage, we have the coordinates. Right? You have z, x, y, z, x1, y1, z1, x2, y2, z2. And the orientations also, there are rules how to orient those. These are the orientations. Now, what matters at this moment or at this stage is that to get a sense of positive, negative, So when you're dealing with a revolute joint, is where you have to think about right hand rule. If your thumb shows the axis of the joint, revolute joint, then when you make a fist, your forefingers show the direction of the positive rotation. And that's why it's shown on this with theta 1, theta 2, and theta.
I think explaining the right hand rule helps best with a, for me, with a current through a wire example.
Yes, we can think about it that way. So if your thumb shows the direction of the current,
this is the magnetic field.
Magnetic field, exactly. Right. Electrical engineering example. Yeah. I think that's basically the main place that, although when we talk about moments, I'm thinking about it now, I'm teaching dynamics and statics. So when we talk about moments, that's where right-hand rule comes into play, when you have cross products. Basically, it's just a cross product, right? Right-hand rule. But in our case, your thumb shows the axis of rotation, forefingers shows the positive direction of rotation. So if you rotate along in theta 1 direction, you're rotating positive. Let's say you're rotating 20 degrees positive. If someone tells you we rotate plus 20 degrees, it means going in theta 1 direction. If they tell you we rotate minus 40 degrees, it means you are rotating 40 degrees in the opposite direction, like in this direction. That's what is important. Sense of positive and negative when it comes to revolute joint. Well, prismatic joints really is pretty straightforward, I think. It's a linear translation, or it's a linear motion. So we can get a sense of positive and negative depending on which axis you are. So in this case, let's look at B2, right? Coordinate frame, this coordinate frame, B2. In this case, since Z2, I'm looking at this right here, and this is a prismatic joint going up and down. It can elongate and it can retract. In this case, it's kind of obvious that when you're going upward, it's positive, you're going the positive direction of Z2. When you're going downward, you can think about it as negative. If we had our coordinate, maybe it's easier to think about it. If we had our coordinates here, y2, instead of putting it down there, which you can do it later on, you'll see. It's kind of optional. If you go upward is positive, you go downward is negative. I think for prismatic joints is it's not really, there is no dispute there. For revolute joint, you have to keep in mind the right hand rule. Your thumb is the axis of your revolute joint, or the positive direction. The forefingers shows where the positive rotation is. Obviously, the opposite of that would be negative rotation. So that's what I want you to keep in mind. We'll see later on. This becomes more important. A couple more examples, maybe not the next one, the one after, because I have a couple of examples that I'll go over maybe this class, or depends if Pamela keeps asking questions. Maybe.
Thank you, Professor.
Yeah, I'm just joking, you know. Hopefully, it makes sense. All right. So we have this robot arm, 2 revolute joints, and there is actually a third one here, 3 revolute joints. You can rotate. This one rotates around this. This one rotates around this. This link there, you see the inner part right there. If I can continue it right here, right, inside cylinder. Right, that some reason my bear with me. All right, so that just, we can think about it as just one part. Now that can rotate with respect to this link. If we have this link, this can rotate, and then it can elongate. So we have 3 revolutes, 1 prismatic joint. The rotation is optional. It might not rotate. It might just, you might have 2 revolute joints and just one prismatic joints. This is a typical SACAR arm, but you can add a revolute there, depending on the mechanism, the way it works. But SACAR itself has two revolute joints and one prismatic joint going up, elongating and retracting. So that's the sense of the way this arm moves. All right. Now, what we want to do is that we want to use what we've learned, right? We want to know that this point O2, all the way at the end right here. Now, that's where you're typically in a robotic arm. That's where your end effector gets attached, right? If you have if this is supposed to grab something from somewhere and put it somewhere else, that gripper is attached to this point. Or if it's just a suction mechanism and it's sucking something, take it from somewhere and put it somewhere else. Typically, a typical motion for SACAR mechanism, it can be just a suction mechanism, right? That's where it's attached. So whatever that end effector is attached to this point. So in a lot of cases, it's important to trace this point. Where is it with respect to this fixed area? Let's say this is fixed to some ground. So it's important to follow that. Important to have the position of this, to have it known at any given moment. Now let's see how can we transform the coordinates of that point, point O2, from the coordinate frame it has, the local coordinate frame, x2, y2, z2, to the fixed coordinate frame, x, y, z, global coordinate frame. You want to think about it that way. So problem statement, you can write it this way. We have SACAR robot arm with a global coordinate frame. Let's skip the coordinate. Obviously attached to the base link. To the base link. So XYZ is attached to link green link, which is the base, is fixed. This link can rotate around the green link. It means it can rotate with respect to obviously XYZ, because XYZ is fixed, attached to a fixed link. To the base link, let's just continue this. To the base link along I'll just continue this sentence and see where it goes. What do I mean by that? Along with base link, along with, does it make sense? With the frame, B1, X1, Y1, Z1, and B2, X2, Y2, Z2 attached to link 1 and link 1 and the tip of link, handwriting gets worse, link 3. Tip of link, I'll get there finally, eventually, link 3. All right, so let's do some notation there. This is the base link that is talking about. This is your base. B1 and B2. So B1 is attached to link 1. This is your link 1. And then you have link 2, and then you have your link 3. This is your link 3, this one inside. Link 3. This I'm talking about. It's is it blue? Not exactly. This link I'm talking about. Right. Obviously, this makes it link 2. I just didn't put link 2 there. I already made this crowded. All right. So that's what the problem is talking about. Now, what is asked is find the position, I'm guessing, find the position of frame B2 and by that we mean i.e. O2, the origin of that. That's going to be O2 eventually. O2 in global coordinate frame. Oh my goodness. In global coordinate frame. All right. So let me clean this up here. We do what we were doing, just because now we are given some fancy notation and it's a robot arm doesn't change anything. We still have 3 coordinate frames and we want to go from the third one or from B2 to G, right? The story doesn't change. It's just now you see we are attaching these frames to a robot arm. And that's where we slowly get into the main story, that why are we even talking about these transformations, right? Now, well, transforming, going from B2, this is what we want. We want the transformation matrix from B2 to G. So basically, it's the transformation matrix from B1 to G multiplied by transformation matrix from B2 to B1. Right. So by the end of the day, you have to find the transformation matrix from B2 to B1 and then from B1 to G. So we'll find each of them separately. Right. Let's find T B1G first, going from B1 to G. Right, or transformation matrix that can transform coordinates of any points in B1 to the coordinate of that point in G. Right. If you remember, we said that before. The transformation matrix is basically just a combination of what we know from before. The rotation matrix, we can think about this as B2. Let's write it this way. Why B1 in G. And then think about this as DG, right, where the origin of B1 is in G, 0 and 1. This is the matrix. You can expand this. So what is our B1G? What kind of rotation do we have? Out of those 3 rotation matrices, how does link 1 rotate around G? Or how does B1, which is attached to link 1, how does that rotate around G? Well, you have 3 options. Right? Rotation around X, rotation around Y, rotation around Z.
What was the question?
So the question is, we want to find our B1G. I want to write these components, right, and expand this into a 4x4. This is a 4x4 matrix, right? 4x4. So this is a 3x3. This is a 3 by 1. You see me writing these, I guess. This is just a 1, and then 1 by 3.
Well, B1 rotates about the z-axis.
About the z-axis, exactly. So B1, this is what we're looking for. RB1G, meaning that how does B1 rotates, and B1 is attached to link 1. So you can think about how does link 1 rotate around G, global coordinate frame. Right? It's just a rotation around z-axis, and G is fixed. So remember, in this case, we're taking G is G, and then B1 is the one that's moving. Right? So if I want to expand this, this becomes rotation around z-axis. So we talked about rotation around z-axis a while ago. Right? What is the angle of rotation there?
Theta 1.
It is theta 1. So B1, again, you can think about the origin of B1 if you don't want to look at the frame. Things are confusing there. O1, just this point, is rotating around this point in z-axis. So it's a rotation around z-axis. It's a point rotating around z-axis. And the rotation is, the amount of rotation is theta 1, whatever theta 1 is. So this becomes cosine theta 1 minus sine theta 1 sine, I have enough room, so let's expand this, sine theta 1 cosine theta 1, right? And this is 0, 0, 1, 0, 0. That was the rotation matrix when we have rotation around z-axis. What is dg? The coordinate of point O1, right, the origin of B1, in global coordinate frame, or the position of O1 in global coordinate frame.
It has to be a vector, right? With like 3 components.
So how do you define it with the values you have?
So is that an L1? So L1, 0, 0, because it's along the x-axis. Is it?
Is it?
Oh, it's L1 cosine theta.
Exactly.
L1 sine theta.
Right? You have to decompose it. Right?
Yeah.
If you think about this as a two-dimensional problem, these are in the same plane. So you decompose this one this way. This becomes L1 cosine theta 1. And this becomes L1 sine theta 1. So eventually, and there is z is 0. It's in the xy plane for O1 is in xy plane. Right? Remember, look at O1. Don't get confused with what's going on there. Look at O1. What is the position of O1 in XYZ, in G frame, in XYZ coordinate? So that becomes L1. Right? We are writing X. So L1 cosine theta 1 becomes L1 sine theta 1. And then you have 0, and the last line is just 0, 0, 0, 1 always. So this becomes the transformation matrix for TB1G. It's a 4 by 4. Next, we have to find a transformation matrix from B2 to B1. Right? That's because we need both of them to get this transformation matrix. And once we know the transformation matrix, we can use that to transform the coordinates of O2 from local coordinate frame to global coordinate frame G. Or from B2 local coordinate frame to global coordinate frame. Let's go to the next page. I'm actually going to bring that here again, just to make sure that we all understand what is going on and what are we doing again. So T B2 to B1. Right? Transformation matrix components, you have a rotation, right, of B2 in B1. You have your D, this D is in B1, so I'll call it DB1, of 0 and 1. Same process. Now, what changes is that you can think about B1, forget about this part now. This is gone. We don't care about this part now. We are focused on this part. Right? We have rotation. We want to know, and to think about rotation, think about point O2, origin of B2. We want to find this rotation matrix. Let me put it right here. Expand this. So, what is the rotation matrix? What kind of rotation do we have? How does O2 rotate in B1?
Isn't that also about the z-axis?
Exactly. It's still about z-axis, right? In this case, z1, but it's still z. Right? We are looking at the origin of x2, y2, z2, and we are following that point. So that point rotates in z-axis, and it rotates with theta 2. Think about it right there. Forget about where it is in terms of z plane. For now, we're just talking about rotation. If you want to think about it this way, I don't know if it makes it easier or not, but think about it this way. The way we were doing this before, we said, well, if local, think about this as global frame now, right? And think about this as local frame for now, because that's what we do for every pair. Now, we were here before any motion happens. Remember, we always said local and global are aligned. So at the beginning, we were x2, y2, z2, right? These two were aligned. Now this is the whole motion, right? x2, y2, z2 go from point O1, which they are O1 and O2 are on top of each other. This is before we have a global frame, and we want to know how can we go from global frame to local frame. Right? There has been rotations and translation. Do you remember we were talking about one rotation, two rotations, and one translation? This is the same story. We had a frame, the frame was here, now frame is here. If I can find it. Now the frame is here. Could be better. This is x2, y2, z2. So the question is, how did we go from global frame, which is B1 in this case, is fixed. How did we go from red, x2, y2, z2, which is the beginning of the motion, right? I'm doing a bad job. That's this one. To x2, y2, z2 green. And remember, we always, when we're talking about transformation, I said you always do the rotations first and make the translation later. How can you go from point O1 to point where red frame is to the green frame? X1, Y1, and Z1 are fixed. X2, Y2, Z2 are or body frame or local frame that can move. It has it went through one rotation, I can tell you that, and one translation to get to where it is at this point, green. So it was aligned with global frame, remember, that was the story. And it now we have a new position for that, which is where the green frame is. Now the question is, what rotation and translation did this red frame go through to get to the green frame? And this is what we had when we were talking about rotation kinematics and motion kinematics. This is just all together. We talked about this in motion kinematics.
So we have the same matrix as before, except with theta 2.
Exactly. The matrix is going to be the same, almost the same. I'll see about the translate, but rotation is the same. Yeah, rotation is the same except theta 2. But what I'm trying to make you think about here is see the red frame and see the green frame. What rotation you go through, or what motion you go through, a combination of rotation and translation, to go from red frame to green frame. If you figure that out, that basically helps you a lot with how to write even this matrix.
You rotate in the positive direction theta 2, and then translate in the x direction L2.
Yes, right. You go L2, but then edge down. But that's basically you have two translation or one translation with two components. But you're right. So the general process here is what you do to get from red to green. So red, which is body frame, is aligned with global frame. Now, if I rotate it theta 2 amount, it's going to end up being here. Right? It's going to be, this is going to be where it ends up. See if you can imagine that. So this is going to be x2, y2, z2. It rotates in positive theta 2 amount. So x2 go in that direction. As a result, y2 rotates theta 2 amount. z2 still stays the same direction as z1. This is theta 2 amount along z-axis. This is our rotation. Now, this one rotation is good enough to get the right orientation. Now we need a translation. Now the translation would be, once you make the rotation, the translation would be going from O1 to O2. That would be your translation. D, B1. Try to see this. I want you to see this. So we start the same story that we were talking about, motion kinematics. Local and global frames, or any two frames you're looking at, right? In this case, B2 and B1, we took B1 as global, B2 as local. That's how it always works when you're looking at two frames. The main one, you can think about it as global. The second one, you can think about it as local, or body frame. Now, they are aligned at the beginning of the motion. Nothing is happening. Nothing has happened yet. We go through all the rotations to make sure that we get the correct orientation of the frame, body frame. In this case, if I just rotate B2 frame, in this case represented by X2, Y2, Z2, along Z1, theta 2 amount, the orientation is correct. Now, blue frame and green frame are oriented the same way. X2 and Y2 are in the same direction. Z2 and Z2, both of them green and blue, and Y2 and Y2, green and blue, are in the same direction. Once the orientation is correct, I move from where blue is to where the green is. So one rotation, one orientation took me from where I was, which basically two frames were aligned, to where I am. And that's the motion you're looking for. That's the transformation you're looking for. So you had the rotation, theta 2 amount about z-axis, z1, which is z in this case, right? So we can write it as cosine theta 2, right? That's just z, rotation about z-axis, minus sine theta 2, sine theta 2, cosine theta 2, 0, 0, I'm in trouble. 1, 0, 0. These three are just zeros. Definitely needed more. Right? This is the translation that we needed to get into the right orientation. So this rotation, sorry. Now we translate the coordinate frame, go from blue to green. That's what we're doing when we do transformation. Right? Always start the body frame where the global frame is, figure out how many rotations you need to make it aligned with the final position of your body frame, right? Make axes align, and then do the translation at the end. So that's how I want you to think about this. Right? So once the blue, once we're in the blue position, remember I was in the red position, I rotated theta 2 amount about z, this is rotation matrix, so I got to blue, orientation is right. Now I can do the translation. Translation would be dB1. So I go from where the origin right now is, this is still origin, is still O2 is here, to where O2, green O2 is, or the origin of the body frame at the current position. Now that dB1, what is dB1? What is, now, what is, forget about everything. Again, things get crowded, but the idea is simple. What is the coordinate? You have a point O2. Tell me what is the position of O2 in X1, Y1, Z1 in global coordinates.
I'm going to take a wild guess here and say L2 cosine theta 2, L2 sine theta 2, and negative H.
That is correct, right? This is just, look at this, right? Remember, D is position of O2 in global coordinate frame, in your first frame. So where is it? This is in three-dimensional space. If this point, you can mirror this, or you can find the projection of that in XY plane. That's where it is. This length is L2. So if you decompose this, go, and then in this direction, this becomes your L2 cosine theta 2. This is your L2 sine theta 2. That's supposed to be theta 2. And then you are down minus H, right? This is where you are in terms of H. This one down. So if this is Z1, remember, everything is written in global coordinate frame, right? Where O2 is in X1, Y1, Z1 frame. H down. So that becomes minus H. This gives you these values. It gives you L2 cosine theta 2, L2, I'm making this here, sine theta 2, and then, let me clean this. And then this is minus H. I didn't think this true about the dimension. This becomes your matrix. Awesome positioning from my side. Zero, 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 one. This should be one. Why did I put 0? Last row is always 0, 0, 0, 1. This is just one. Nothing to do with the rest of them. All right. So it's pretty simple geometry. Seems complicated, but you just have to see and keep in mind the definition of what you're looking for. We are looking for a transformation matrix that transforms the coordinate from the second frame to a first frame. The second frame, always think about it as body frame. The first frame, think about it as global frame. Right? In a pair of frames that we always do in pair, right? Start with, think about it this way always. Start with where your local frame is. Your local frame is always aligned with your global frame at the beginning of the motion. Figure out what rotations and what translations you need. Right? Typically, you need one translation. Almost always, you need one translation. Depending on the situation, more than one rotation. Sometimes just in this case, you do one rotation and one translation. You go where you should be, where your body frame is. Sometimes you have to do multiple rotation, two rotations, and then one translation. That's how you get your transformation matrix. We'll do more examples on this. This has to be understood. Right?
Professor, I have a question.
Go ahead, Paul.
In terms of like from what we have from our figure, how will we know where the links or along with the joints are rotating either through clockwise or counterclockwise? Because wouldn't that change for our translation, our cosines and sines?
So a good question. Generally, we write the equations in just general form. Not generally. We write the equations in general form. I think what you're trying to say that what if it was rotating this way, right? Like theta 2.
Yes.
Well, what happens is that mathematics of the problem takes care of it. You're using sine and cosine, so it's going to be cosine some negative angle, right? If it was rotating this way and your end frame was in a way that was like in negative direction, your theta 2 as negative, cosine of a negative angle, as long as you're in the fourth quadrant, is still going to be the same length. Sine is going to be negative. So don't worry about that. The mathematics of this formulation is going to take care of that positive negative. We always write it with this positive sense, at least most cases. You might see a few exemptions when I go further and get into specific mechanisms. There are ways. So these transformation matrices, you'll see that for a 2x2, we get into a matrix with a couple of elements. And then remember from last class, we totally opposite. I used this review math from math before, sine theta 1 plus theta 2, cosine theta 1 plus theta 2 to simplify that matrix. Right? Now, there are tricks in defining these coordinates in a way, or positive negatives in a way, that sometimes we make exceptions and we orient things in different ways to get a matrix that we can simplify. But as a general rule of thumb, you don't need to be, as a general rule, you don't need to be worried about positive negative. Right? Always go with positive. Right? At least in this course, I can tell you, you don't need to worry about it. If you get into robotics and very complicated, more advanced, I would say, stuff, you will see why sometimes they make those exceptions to get just get the math right and make it easy to solve most cases. Not the physics of the problem doesn't really change. All right, so we were working for TB2G, right? So TB2G is now that we have TB1G times TB2B1. Right, if you do the multiplication, this is a 4x4 matrix there. The other one is also a 4x4 matrix. So you just multiply these two. first row, first column gives the first element of the first row of the finite matrix, first row, second column gives you the second element of the first row of the finite matrix, and go so on and so forth. If you do that multiplication, you'll get you will get this one. I'll try to write it quickly. Basically, this becomes cosine theta 1 cosine theta 2 minus sine theta 1 sine theta 2. I'm in trouble. Let me just move it down. No way that I can fit this thing. Make it right here, so don't worry about hopefully the spacing. So this becomes cosine theta 1 cosine theta 2 minus sine theta 1 sine theta 2. The second element becomes this is a SACAR, so minus cosine theta 1 sine theta 2 minus sine theta 1 minus sine theta 1 cosine theta 2. Then this is just 0. Oh, that's long. This becomes L2 cosine theta 2 cosine theta 1 minus L2 sine theta 1, right here, sine theta 1 sine theta 2 plus L1 cosine theta 1. Let me double check. L2 cosine theta 2 cosine theta 1 minus L2 sine theta 1 sine theta 2 plus L1 cosine theta 1. Second row becomes sine theta 1 cosine theta 2, right? Sine theta 1 cosine theta 2 plus, then we have sine up, so it becomes cosine theta 1 sine theta 2, right? And this is supposed to be 2, and this is minus sine theta 1 sine theta 2 plus cosine theta 1 cosine theta 2. This is 0, and we're almost there. L2 sine theta 1 cosine theta 2 plus L2 cosine theta 1 sine theta 2 plus L1 sine theta 1, and then we have 0, 0, 1, 0, and then 0, 0, 0, 1. You can simplify this following exactly the same math. Let me double check this one element. Sine theta 1 cosine theta 2 plus cosine theta 1 sine theta 2 minus sine theta 1 sine theta plus cosine theta 1 cosine. So you can simplify this, right, from what we did before, similar to this math. Similar to what we did here before, right? I will get this to work eventually. Okay. You can rewrite this as sine theta 1 sine theta 1 plus theta 2 cosine theta 1 plus cosine theta 1 plus cosine theta 2. So I can just give you the final answer and you give it a shot and see if you can figure that out. You should be able to do that. This becomes cosine theta 1 plus theta 2. Obviously, this is the easy one. You factor out 1 minus. This becomes minus sine theta 1 plus theta 2. This is just 0. Right. This one, you have to factor out L1 cosine theta 1. We cannot do anything about it. But this part, we can write it as L2 cosine theta 1 plus theta 2. Same story here. This one, you can just write it as sine theta 1 plus theta 2. This one, straightforward, cosine theta 1 plus theta 2. I cannot do anything with L1 sine theta 1. I missed this one. This should be H, right? We had minus H there. I forgot about that. Shows up here. I can give myself more room. Nobody's stopping me from doing that. Minus H. So this one, you factor out, this becomes L2 sine theta 1 plus theta 2. Now, you had just have the transformation matrix. Now, what was the process? Half of you probably lost by now. That why were we even doing this? We wanted to find the position of frame B2 in global coordinate frame. Right? So this frame right there, and by that we mean the origin of that frame. We wanted to find the position, this position in G. Now that we have the transformation matrix from B2 to G, all you need to do is to multiply the find the position of O2 in frame B2 and use a transformation matrix to take it back to global coordinate frame. So here is what we want to do. We want to go from, so I want RG. I think I jumped from that page very fast if you were taking the notes. I can just wait a minute.
Quick question / observation. So
Right.
when we created both matrices for like each whatever situation, we had, so like if you look on the left, it looks like it's like a rotation about the z-axis, except we have theta 1 plus theta 2.
Mhm.
Do you see that? So like,
Yeah.
could I just skip the step of writing out all these sine cosines when it seems like it's just the case of,
Well, if your
Matrix.
frames were not oriented in this direction, you wouldn't have gotten this, right? We'll get to that. That's why they define these frames in this way. So you end up having
okay.
a nice thing. But if your Z1 was not in the same direction as Z, or your X2 was not in the same, was in the orientation of your frame was different, you won't end up having this. So this is the geometry that we defined to get this nice, eventually final matrix that, as you realize, is basically just a rotation about Z-axis, but with two thetas.
Yeah. Okay.
So it's not that obvious. Let's put it this way. Almost never that obvious. But you will see later on that actually the equations for famous mechanisms are already derived. Right? In so many cases, you just have to define the right coordinate frame. And if you do that, they say, well, with these coordinate frames for this SACAR robot arm, this is going to be the transformation matrix for you.
Okay.
Right? In literature. Not in this course, you're going to end up finding them, but generally they are available. And don't be discouraged by the math. As I said, this is the maximum we go, just 3 frames. Above this, we all do it, we do it with Mathematica and do the math with Mathematica, which you'll see makes your life much easier. It even does the simplification. So you don't need to do, as long as you find the transformation. What I want you to be able to do is find the transformation matrix between 2 frames. That's the important step that no software can do for you. If you do that, right, the mathematics of it, you can use any software. You can just multiply this and simplify that and get the transformation matrix, as long as your transformation matrices between frames are correct. That's the part that is valuable. The math of it, any computer can do that for you. So I'm going to again bring that here. Spend quite time on this one. So we are trying to find the coordinate of, or we want to find O2, where O2 is in global coordinate frame, this position, which basically we can find it by G B2 and or B2 O2. We already know this matrix, right? This is the 4x4 matrix we just found in the previous slide, the previous here, right there. This is, we found this. what we need to know is this one. All right, so what is this one? What is the position of O2 in frame B2? What is that vector? Oops. I can do a better job. What is that? Forget about everything else. Just tell me where O2 is in B2.
O2 relative to B2 is negative H, 0, 0, negative H.
No, it's 0, 0, 0.
Oh.
Right? It's O2 is just the origin of B2, right?
Oh, that's right. I keep thinking that everything's level with G.
No. We are looking, just forget about everything else. We're looking at point O2. Where is the what is the coordinate of O2 in X2, Y2, Z2, which is basically 0, 0, 0.
Right.
Don't overthink things. Overthink things, folks.
Well, my brain automatically just saw everything as level.
I understand. That's why I asked, because I knew that. I guess that's that can be a point of confusion.
It doesn't help when you keep scribbling all over this drawing.
Yeah, I have to stop myself.
No, I'm kidding.
All right, so the position of the origin is 0, 0, 0, right? Just that's where it is. So you can find where that origin is in global coordinate frame, or again, our O2 in global coordinate frame is T B2G, which is a 4x4 matrix, times your R. Let's put the R here as nice as I can. So 0, 0, 0, 1. This is a 4x4 multiplied by 4x1. So you're going to end up having a 4x1, which gives you where the RO2 is, and that will give you the coordinates of this. You want to find, I can think about it this way. You want to find X2, Y2, Z2. Position of O2 in frame G. Right? So if you do that multiplication, you're going to end up getting, I'll just give you the final answer because I can't really type it here. I'll give you this vector, L2 cosine theta 1 plus theta 2. You basically get what you had in the last L1 cosine theta 1. This should be L2 sine theta 1 plus theta 2 plus L1 sine theta 1 minus H, and that 1 is always 1, has nothing to do with what's going on. In this case, maybe you can tell me that I could even probably guess this by looking at where the coordinates are. If you're good, if you could, good for you. I probably couldn't. But this becomes your X2. This becomes your Y2, and this is basically your your Z2. This is the position of the origin or the tip of link 3 in global coordinate frame. Now, if you have a tool tip, or whatever tool is that, whatever mechanism you're designing, and you want to control its position at any given moment, here is the analytical equation for you. How to control theta 1. It tells you what theta 1 and what theta 2 and what L's you should have, what H you should have to reach a specific point in your workspace, right? Let's say if it's on a table, you want to reach out, and where your arm is your origin. You want to reach out to a specific point, pick something, place it in another point. As long as you know those coordinates, how can you play around with your theta 1 and theta 2 and H to be able to get there, move, put it where you want to put it. Right? You have a full understanding of the kinematics of tip point. All right, just going to stop here.